Good morning, good afternoon, or good evening, depending on when you're watching this. We're in chapter 2 and we're getting ready to dive into quantum mechanics. Want to remind you where we are, what point we're at when we start to look at quantum mechanics. Heisenberg gave us the Heisenberg uncertainty principle that said that you cannot know the exact location and the exact velocity of a particle at the same time. Essentially, the more you know about one, the less you know about the other. So you're forced to choose. What do you want to know more about? Velocity or position? Okay? And that brings us to the difference between deterministics and probability. In deterministics, the present determines the future. So if I throw a baseball, I can map out a trajectory for that baseball, and where it launched from and the speed and the direction I launched it tells me where it's going to land. Probability is the statistical pattern of likely outcomes. So if I throw an electron, okay, I can't tell you exactly where it's going to land. I can just say it's somewhere in here. So there's a difference in your approach. And what we've discovered with electrons, things that small moving inside the atom, deterministics doesn't work. And we have to take a probability or statistical approach. And one of the reasons that we have to deal with this statistical approach is because down in the world of the itty-bitty, the world of the electron, okay, we see both a wave behavior and a particle behavior. It's called the wave-particle duality. And because of the wave-particle duality and the smallness of the smallness of the particles that we are trying to observe, okay, we can't know it all. Okay. So image-wise, think about it. Here's a classic trajectory. Okay. Here's a quantum mechanical probability distribution. Roll it down for me. So, with electrons, we can't have our cake and eat it too. That brings us to quantum mechanics. We've accepted that we can't know exact location and exact speed of an electron. And the energy of an electron is associated with the speed of the electron. Kinetic energy is equal to 1/2 mv squared. Don't panic, you don't have to do any calculations with that. And since energy is associated with speed, we're actually more interested in energy than we are in position. So we're going to concentrate in on answering as much, in much detail, what kind of energy an electron has and not worry as much about the position of an electron. We're going to accept uncertainty in position. So for a position, we're going to use a probability map. Now, what do I mean by a probability map? A probability map is a region of space where the electron is supposed to be 90% of the time. Example. My Aunt Marge lives in Lexington, Kentucky. So with about 90% reliability, I'm pretty sure she's in Lexington, Kentucky. I don't know exactly where in Lexington, Kentucky she is right now, but she's in Lexington. She could be sneaky and have gone somewhere else for the day, but my Aunt Marge is 86 years old and she's not going much of any place right now. So I'm pretty sure with a 90% probability she's in Lexington. Okay? With Heisenberg's uncertainty principle, people started trying to look for approaches to explain the energy levels of electrons inside the atom. And remember that Bohr said there's only certain allowable energy levels. De Broglie mapped out and proved that there was a wave behavior. So Schrödinger said, I'm going to deal with probability, and I'm going to deal with the fact that electrons have wave behavior. And he came up with what was called the Schrödinger equation. Now don't panic, this is high-level differential math, so we're not going to do any calculations with it. But his equation was H psi E psi. H is called the Hamiltonian. It's a mathematical operator. E is the energy level of an electron. Psi is the wave equation for that electron. Okay? A plot of psi squared is the probability density distribution for an electron, and we call that an atomic orbital. An orbital is different than an orbit. An orbit is a flat circular pathway. That's what Bohr had in his model. But an orbital is a volume of space where 90% of the time the electron is going to be. Okay? It takes four quantum numbers, to tell us the energy state of an electron and to give us its probability distribution. So we're going to talk about the four quantum numbers. The first quantum number is called the primary quantum number. It's an integer, 1, 2, 3, 4, 5. It's commonly called the shell number. So I'll talk about what is the shell. What is shell number? What shell is the electron in? The things that the primary quantum number does for us is it tells us the size of the orbital. The higher the primary quantum number, the shell number, the larger the volume of the orbital. So if we start thinking about them being kind of stacked, okay, let me draw a picture for you. Okay, make sure I've got it lined up over here on the sideboard. So if I had an orbital with n equals 1, okay, it would be this size. The next size up orbital is going to be bigger, n equals 2, and that's everything in there. We'll be talking about shapes in a minute. When we get to n equals 3, it's bigger through, and it's everything in there. Okay? So the larger the n value, the larger the orbital is going to be. Now, we start by thinking about the hydrogen atom. Okay? When we think about the hydrogen atom, hydrogen is that really simple system, 1 proton, 1 electron. So hydrogen is really easy. All orbitals all electrons in the same shell in hydrogen have the same energy. So all orbitals in the same shell have the same energy for hydrogen. And hydrogen only. Every other atom actually takes 2 quantum numbers to uniquely identify or give you the energy of the orbital. Okay? The maximum number of electrons that can be in any given shell is 2, n squared. So in the n equals 1 shell, okay, n equals 1 shell, number of electrons max is 2 times 1 squared, which is 2. If n equals 2, then I have 2 times 2 squared, so that's 2 times 2 is 4, times 2 is 8. When n equals 3, I get 2 times 3 squared, so 3 times 3 is 9, times 2, that's 18. And if we go up to n equals 4, I have 2 times 4 squared. 4 squared is 16. 16 times 2 is 32. Okay? So you see a pattern here. All right? Okay. Now let's talk about the second quantum number. The second quantum number is called the angular quantum number. The symbol for the angular quantum number is L. Okay? The values that L can have depend on the value of N in the shell. So the shell number controls the number of subshells that it can have. The value of the angular quantum number, also called the subshell number, varies from 0 up to n minus 1. So the value that L can have, the subshell number can have, is limited by the value of n. All atoms other than hydrogen need both the L and the n value, two quantum numbers, to determine the energy of the orbital, okay, and therefore the energy of the electron. So it takes two, I repeat, two quantum numbers to determine the energy of an orbital. So the number of subshells in a given shell equals the value of n. So the first shell only has one subshell. The second shell has two subshells. The third shell has three subshells, so on and so forth. So if we look at the value, when n equals 1, L can be 0 up to 1 minus 1, which is 0. So when n is 1, the only value that L can have is 1. Okay? So the first shell only has one subshell. When n equals 2, then L can be 0 up to 2 minus 1. So that's values of 0 and 1. So the second shell has two subshells. The third shell, n equals 3, my L can be anywhere from 0 up to 3 minus 1 in integer steps. So that means I have 0, 1, and 2. So let's try 4. Okay, n equals 4. If n equals 4, L can be anywhere from 0 up to our value of n minus 1. So n, which is 4, minus 1. So it can have values of 0, 1, 2, or 3. So the fourth shell has 4 subshells. So if I got up to the fifth shell, n equals 5, L could have values of 0 up to 5 minus 1. So it could have values of 0, or 1, or 2, or 3, or 4. Okay? Now, the value of L does a couple of things for us. Okay? One, it helps us determine the energy of the electron. Very important. The other thing that L does for us, the subshell number, is it's going to tell us something about the shape. Now, subshells are so important, they have common names. When L equals 0, we call it the S subshell. And any orbital in the S subshell is called an S orbital. When L equals 1, we call it the P subshell. Any orbital in the P subshell is called a P orbital. L equals 2 is called the D subshell, and L equals 3 is called the F subshell. We will not worry about common names beyond the F subshell. So L equals 0, S, L equals 1, P, L equals 2, D, L equals 3, F. Not only does the L value help us lock down the energy, like I said before, and for all other atoms other than hydrogen, but it also tells us the shape of the orbital. So let's talk about shapes. Okay, now when we talk about shapes, the first one we're going to talk about is when L equals 0. Okay, when L equals 0 and we've got the S subshell, we're talking about an S orbital. And let's look at probability density. Scroll. Go the other way. Yeah. Go down just a little bit. Right there. Perfect. Now, here's a graph that shows psi squared as a function of radius. So notice as you move out from the nucleus, away from the nucleus, the probability of finding the electron goes down. Okay, scroll up so I get this second graph. Very good. In this second graph, what they've done is a radial distribution. So instead of taking a straight line out, they have given you the density at circles. So if I'm at a distance 200 picometers from the nucleus and I add up everything on the spherical surface there, that's what the probability density is. Notice that it peaks and comes down. That's the maximum probability, is at 52.9 picometers. Interestingly, when Bohr calculated his radius for his orbit for hydrogen, what he was actually getting is the radius for the most probable distance for the electron from the nucleus at a certain energy. So he got something useful, he misinterpreted what he got. For the s orbital, it turns out that the shape of the orbital is a sphere. Okay? So a nice 3D sphere, 1s. So an s orbital is a sphere. Okay? If we move on to the p orbital, p orbitals are kind of neat because p orbitals have a dumbbell shape. Now, previews of coming attractions. In the d subshell, in the p subshell, there are actually 3 orbitals. And I want you to notice that they have this dumbbell shape. One sits along the x-axis, one sits along the y-axis, and one sits along the z-axis. Notice that the probability density looks a little bit different for the p orbital than it does for an s orbital. Also, I want you to notice this dead zone here in between the 2 parts, the kind of dumbbell ends or the teardrop ends. There's a dead zone. Remember, when we're dealing with quantum mechanics, we're dealing with wave equations. And 2 waves can add together to cancel each other out, to give us destructive interference. This dead zone, which is called a node, is a place where the electron waves add up to give us 0. And it's called a node. So I can have the electron wave causing a disturbance here, an electron wave causing a disturbance here, and have a dead zone in between. So it's kind of one of those mind-blowing things. Electron density is here, electron density is here, but it's never in between. And you're sitting there going, but how does it do that? Well, it's a wave. So remember that electron can show both behaviors. So we talk about the P being a dumbbell shape. Now let's look at D. D orbitals have what I refer to as a 4-leaf clover shape. They have 4 petals, like the leaves of a 4-leaf clover. And it has 2 nodal planes. Okay? This crisscross here, where there's no electron density or no, the waves add up to be 0, and here, where we get 0. And notice there's one in this plane, this plane, this plane, this plane, and there always has to be an odd duck somewhere, okay? This is a d orbital that's got a really weird shape. It's kind of got a dumbbell donut shape. I don't want you to worry about the dumbbell donut shape. If you tell me that a D looks like a 4-leaf clover, a d orbital, I'm going to be happy. Okay, scroll up for me. Okay? Now, we're not going to worry about the shapes of the f orbitals. They are just too complicated for us to worry about. It just gets really wild. So, to identify a specific subshell, it takes 2 quantum numbers. You've got to have a shell number and a subshell number. And one of the ways we make it easier to write, okay, and compact, is to use a pattern where we use the shell number and the subshell common name. So if I write 1s, that means, 2s, that means n is 2 and L is 0. If I were to write 4p, that means that n is 4 and L is 1. If I wrote 5d, it would mean n is 5 and L is 2. So let's try writing some things on our own. I'll try. Okay, so let's say that I were to write 3s. If I write 3s, that means that n equals 3 and L equals 0. If I were to write 3p, that would mean n is 3, but L would be 1. And if I were to write 3d, that would mean n is 3 and L equals 2. Okay? Now, remember there are limits. The value of L limits the value that m sub L could be. So when n equals 1, the values that L can have are 0 and 1. And RZ is 0 and S. When n equals 2, L can be 0, S, or 1, P. When n equals 3, L can be 0, or 1, or 2. So 0 is S, 1 is P, 2 is D. When n equals 4, L can be 0, 1, 2, or 3. So we've got S, P, D, and F. Okay? So I can see what the value of n is limits the value of L. Now, all orbitals in the same subshell are said to be degenerative. When we use the word degenerative, it means that they have the same energy. So if I have more than one p orbital, hint there are 3, they're all going to have the same energy. For a hydrogen atom, all orbitals in the same shell are degenerate and have the same energy. So for hydrogen, every orbital in the second shell has the same energy. But if I'm looking at a copper atom, every electron in the same subshell has the same energy. So there's a difference. Hydrogen is a different beast.
We'll do it. Yeah.
Yeah. Ooh, we're fancy. Okay.
Maybe a little too fast. Oh.
Yeah, well, I'll figure it out. Okay, so magnetic quantum number. Our third quantum number is the magnetic quantum number. It's given the symbol m sub L. M sub L can have values from -1 integer steps to 0 up to plus L. So minus L to plus L in integer steps going through 0. M sub L, the magnetic quantum number, okay, is called the orbital number. It's the common name. And the values that m sub L has, you can see, are limited by the value of L because it can run from minus L through 0 to plus L. Okay? Now, what the magnetic quantum number does is tells us a specific orientation of 3D space for a specific orbital. It's kind of like giving you your hotel room number. So the shell number is like saying I'm in the Holiday Inn. The subshell number is I'm on the second floor. The magnetic quantum number says I'm in room 30 on the second floor. Okay? So you're getting more specific in your addressing, telling you where things are. All orbitals, again, in the same subshell have the same energy and are degenerative. Okay? So let's look at some numbers. The third quantum number uniquely identifies an orbital. The maximum number of electrons that can fit in a single orbital is 2. So let's look at some values of L and what the value of m sub L that goes with them are. Okay, so let's play at the whiteboard again. Now let me make sure that I've got everything lined up here. Remember, guys, I'm my own cameraman. Okay, so we got things lined up there. Now, when L is 1. Well, no, let's start out with L equals 0. So we have the S subshell. That means that M sub L can go from 0 through 0 to 0, which means only 0 is the value. So the S subshell only has one orbital in it. So M sub L here is 0, one orbital. Okay? Second shell, the S orbital the S subshell only has one orbital. But when I come to the P subshell, where L equals 1, M sub L can be -1, 0, or +1. So -1, 0, +1. So the P subshell has 3 orbitals. When L equals 2, we're talking about the D subshell. M sub L can be -2, -1, 0, +1, +2. So let's look down here in the third shell. When I have the S subshell, it's only got one orbital. The P subshell has a -1, 0, +1. The D is -2, -1, 0, +1, +2. So notice the N equals 3 shell has 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. Each can hold 2 electrons. 9 times 2 is 18. And remember when we took 3 squared and multiplied by 2, we got 18. Okay? Number of orbitals. Well, number of electrons. All right. And then when we get up to L equals 3, M sub L can be -3, -2, -1, 0, +1, +2. You guys can write that out for the 4th shell. Okay? So let's scoot back over here and look at our screen. All right, we have it good and lined up. So one more time. Notice when L equals 1, -1, 0, +1, which means the P subshell has 3 orbitals. The L equals 2, which is the D subshell, has 5. L equals 3, which is the F subshell, has 7. So notice it went 1, 3, 5, 7. So if we went up to L equals 4, we'd add 2 more on. We'd go to 9. So the number of subshells in a shell equals N. Number of electrons maximum in a shell is 2N squared. Number of orbitals in a subshell is 2L plus 1. Number of electrons maximum in a subshell is 2 times 2L plus 1. Okay? So orbitals exist inside subshells. All orbitals in the same subshell are degenerative, and subshells exist inside shells. So you can think about this as being kind of layered. Shells, subshells, orbitals, kind of like giving an address. What town, what street, what house. Okay? So if we look at allowable combinations of quantum numbers to describe an atomic, if we look at the combinations of quantum numbers that describe an atomic orbital, we can see that each successive quantum number depends on the quantum number that preceded it. And there are only certain allowable quantum numbers that are valid. Okay? For example, when n equals 2, the only values that L can have are 0 and 1. And by the same token, when L equals 1, then M sub L can only be -1, 0, and +1. Okay, scroll up. So let's look at these set of quantum numbers and decide which ones are valid, and then what their common name would be. So if we look at this first one, when n equals 1, the only value that L can have is 0. So this is not a valid set of quantum numbers, so not valid. Okay? When I look here, when n equals 3, L can be 0, 1, or 2. 0 is good. When L is 0, M sub L has to be 0, and that it is. So this is a valid set of quantum numbers, okay, to describe an orbital. So this would be a 3s orbital. A 3s orbital, because I've got an orbital in the s subshell. Now let's look here. When n is 2, can L be 1? Well, n is 2, L can be 0 or 1. When L is 1, can M sub L be 1? When L is 1, it can be minus 1, 0, or plus 1, so that's valid. So this is a 2p subshell, okay? 2p. So this is a 2p orbital. When n is 1, can L be 1? Answer is no. When n is 1, the only value that L can have is 0. So this is an invalid set of quantum numbers. So the first one here was invalid, the second one is invalid, the last one is invalid. This one is a 3s and this is a 2p. Okay? Now shapes of orbitals one more time. S orbitals are spherical in shape. The 1s orbital is smaller than the 2s orbital, which is smaller than a 3s orbital. So as n increases, so does the size of the orbitals. Okay? Now, we'll notice that in the 2s and 3s orbitals, we'll see probability points where it goes to 0, spherical nodes. This is, again, remember, related to the wave behavior. So scroll up for me. Okay, let's look at some pretty pictures here. What is showing right here in the graph is the 2s orbital and the 3s orbital in a given atom. 1s would be a solid sphere, smaller still. But I want you to notice that there is this point where the probability density goes to 0. That's referred to as a node, and it's due to the wave behavior. The second shell has 1 node. The 3s orbital has 2 nodes. If we had a 4s orbital, it would have 3 nodes. Don't panic. I don't expect you to have that memorized. But I want you to understand that every successive s gets bigger. Okay? Now let's look at p's for a minute. The p's have 2 lobes, and their electron density is dumbbell shaped. They've got those nodal planes, and they're going to stack just like the s orbitals do. The d orbitals have that cloverleaf shape, and they have 4 lobes, and so they have 2 nodal planes. Okay, and d orbitals stack just like s orbitals do. Okay, now this is a very nice picture. What you've got to remember is that these electron waves in different orbitals share space. So everything that's in 1s orbital for an atom is also incorporated into 2s, which is incorporated into 3s. Okay? And that the d's and the p orbitals overlap and pass through kind of the space that the s orbitals do. So that you get kind of these spherical electron clouds when you look at all of the electrons in an atom at one time. Now let me draw you some pictures over here for a sec. Okay? I'm going to erase the numbers. Okay. If this black dot is the nucleus and it's way oversized, here would be my 1s, and then here would be my 2s. Okay, now 2p is the same size, in other words, has the same maximum travel from the nucleus as the 2s, but it's got, you know, this is a 2px and this is a 2py. And this whole thing is py, px, pz would be coming out of the board. Okay? If I go up to the third shell, there's 3s, and then here's 3px, there's 3py, and I know it's not a perfect drawing, and then the d orbitals come in. So I would have these in there too. So you can see how it all starts stacking up on each other. Electrons are very tiny, remember, and we're talking about their wave behavior, and they can very easily pass through the same region of space. So don't think about the orbitals as being mutually exclusive. They kind of have tracks through each other. Okay? Now, it's time for us to meet the last quantum number.